Very good. Okay, so we're still at the beginning of the course. We are going to be finishing up very soon. This is all on background foundations, things that when you're tickety-talking on the on your keyboard, writing SQL queries and stuff, that's good. It's good to know, and that will actually take up most of the course, is how to make queries in the correct way. But before you start really writing queries for databases, I think it's really important to have some type of background and knowing what's happening a little bit behind the scenes. So we're building up to all of this, okay? Um, it might feel like we're kind of hitting different places along the way. I don't know of any other way to do it. There's a lot of different areas that all kind of overlap, and once you're familiar with a few of them, you'll have sort of a tapestry of knowledge uh, to pull from. Okay, so we're talking about data structures. I'll remind you that a data structure is different than an algorithm. If you take computer science courses, these are two separate things. A data structure is just the way you organize data. And different data structures have different benefits or different drawbacks. An algorithm is how, given some input, how do you produce a certain output? So one simple example is sorting numbers. Given a list of unsorted numbers, how do you output a sorted list of numbers? And there's lots of ways to do it. You could probably, without any type of education whatsoever, come up with your own algorithm that will work always. It might not be the most efficient, but it'll work. In any case, taking an input and producing an output is an algorithm. A data structure is just a way of organizing your data. This can be on paper, which is what we'll be talking about in the beginning with the binary tree. Everything is just on paper. Okay, I'm drawing nodes and edges and stuff like this. Then there's the way that how do you realize this data structure on real world hardware? Okay, so we're going to be talking about trees, binary trees to begin with. In the end, we'll be talking about something called B trees, which are an upgraded version of binary trees. But if you're comfortable with binary trees, all of the extra B tree stuff is just kind of details. It's garnish on top of everything. So we're going to start with the slightly simpler thing, just binary trees, and we'll end up at B trees. Okay. So I forget. I know I've showed this to. I'm teaching another class, and so sometimes, sorry, I get them mixed up a little bit. I think that I've showed off these things to you: memory, that's RAM, a solid state disk, a small kind of laptop mechanical hard drive, a bigger mechanical hard drive, and an SD card. All this. So there is a way that on any of these things you can put a tree there, and that's part of what we'll be talking about today. Okay. 1个小时. Okay. All right. Good. So did I talk in detail about these things with this class? These like hardware pieces and stuff. This stuff. Yes. Good. All right. All right. Well, then I won't go into the whole spiel again. I might just touch on it at some point later. In any case, like that's real hardware, and that's where data is going to go. And there is a way to take these things like a tree, where I'm drawing it now, I'm calling it on paper. There's a way to have this on those types of devices. Same data structure, it just looks a little different. Okay, so we'll talk about that. So here on the screen, Just quick vocab for trees. We can talk about the root of a tree. Everything starts at the root. When you're searching, when you're inserting, whatever, the start point is at the root, and from the root you go down the tree until you can't go any further. Therefore, the depth of the tree is the most important quantity about it. Because you start at the root, and then you work your way down the tree until, in the worst case, you hit the bottom. From the journey from the top to the bottom is the depth of the tree. So that's for trees, we care about depth. For arrays, we care about length. Question? No. All right. Sorry, phone caller. I'm going to mute you. All right. So in trees, there's things called parents and grandparents. A child is so-called if it's one level below the layer above it, and there's an edge connecting them, then that's a child. Likewise, this child has its parent. This parent can have a grandchild, great-grandchild. You can talk about a node's ancestors, the chain upwards to the root. Those are its ancestors. You can talk about a node's descendants, which is from that node in the tree, every single node from its children, grandchildren, great-grandchildren, everything, that subtree. You can talk about a node's descendants, and everything is sort of comes from the idea of like a family tree. Leaves are nodes with no children. So they appear at the bottom of the tree, but you'll notice, for example, in this tree, there's 4 leaf nodes, and when you're talking about things at the bottom of the tree, it's kind of not as clear. I prefer thinking of it as leaves are those nodes with no children. No matter what level they are in the tree, you could have leaves. All right? Okay. So we talked about binary trees. A binary tree is one where you have data that can be sorted. Okay, so there's things that are bigger, there's things that are less than. If it's just random data and there's no concept of something being bigger or smaller, you don't use a binary tree. Okay, a binary tree is binary because there's 2 children, and it's a binary choice which child you would, or which direction you would go to. You break left, for example, if you're less than or equal, and you break right if you're strictly greater than. And then there's nothing else. You're either greater than or you're less than equal. So that's a binary choice, and that defines whether or not you go left or right when you're traversing the tree. All right. Then we talked about balanced binary trees. And balanced binary trees are more important. Well, I won't say more important. They have an extra few benefits that make it worthwhile to try to maintain balance in your tree. Similar to when we were talking about arrays, or is it here? When we were talking about arrays and how to do a search with an array, you can do a linear search where you start at the beginning, until you find whatever it is you're looking for, and then your data doesn't need to be sorted at all. That search works. It takes linear time. That's time n. If you have n things, in the worst case, it will take n steps to find what you're looking for. Or you can do a binary search. You can do a binary search where, except now you need the numbers sorted. So if you're given an unsorted list, you need to waste some time to put everything in sorted order. Once you've wasted that time, now you have a sorted list, and you can do a binary search. So if you're looking for something, you cut straight to the middle of the list, see, is it there? If not, because the list is sorted, you know that you're going to either continue your search with things on the right, or you're going to continue your search with things on the left. And whichever direction you decide to continue your search, everything else, you can just forget about it. You never need to look there. So a binary search is a lot faster than a linear search. But it comes at the expense of needing to sort your data, which is a bit of a time waste in the very beginning. But once it's sorted, you can do faster search. Similar to that is with trees. It takes time to keep your tree balanced, to make sure that trees like this one on the right don't appear, where you get these really long chains, because then the trees, they don't really benefit from the tree structure. They just kind of work like arrays. But if you take some time and you rearrange all of the nodes so that the tree is as shallow as possible, if you take time in the beginning to do that, and then you take time to maintain it, then you get some benefits, like faster search, faster insertion, faster deletion. Okay, so it's okay to waste time in the beginning, even if it's a fairly long time. If later something you're going to be doing again and again and again and again goes faster, like search. With databases, we're mainly concerned about gigantic amounts of data and searching through it quickly. Among all of this data, return to me the data of this type. And you don't want to be, waiting an hour or two for results on that. You want it to happen 5 seconds or less for a big amount of data. So it doesn't matter. I mean, like if it would take you an hour to do a search without doing anything to your data, or you could spend a week organizing all of this and doing the trees, but now it takes 30 seconds to do a search. That's a week worth wasting, because we're going to be doing search again and again and again and again, day in and day out. So let's waste time in the beginning. Those are exaggerated numbers. It doesn't take a week to do it, but I'm just making a point. All right, let me pause and open up the floor for questions about binary trees, balanced trees, trees in general, anything at all.
Can you hear me?
Yeah.
I just wanted to confirm, so for balance, that means the previous level has to be full.
Yeah.
Okay. Okay, thank you.
Yeah, that's right. Yeah. So the previous level has to be full before you begin a new level. Yeah. In other words, the tree is as shallow as possible. There's no empty spaces above you. If there is an empty space above you and you're being added to the tree, you should occupy one of those empty spaces first. Don't dig deeper into the tree.
Okay, thank you.
Oh, full just means each node has exactly 0 or 2 children. Yeah, right. So every node has exactly 2 children, except for the leaves, which have 0 children. Oh, I'm sorry. No. That's not quite right. That's not quite right. A full tree is one where the bottom layer and all layers above it are completely occupied. All right. Let me give a quick example of this. So, fitting the definition that you gave, for example, this is not a full binary tree. It's true that all nodes have exactly 2 children or 0 children, but it's not full because the last layer has to be full. So you could rephrase it a couple of ways, but the last layer has to be full, or all of the leaves have to appear on the same level. There's no empty spaces above, and the last layer is full. So that is a 3-layer full tree. Here is a 2-layer full tree. If we wanted a 3-layer full tree, Again, this is not full because we still have empty space on the bottom. This would be a full tree. Everything on the bottom here are examples of full trees. Any other questions? No. All right. Then let's continue. Let's see. Full trees. Example. Example not full tree. All right, whatever. You can come up with your own examples too. All right. So, there's two things that I want to cover. I'm trying to figure out what would be the best order. Well, let me ask, would you guys rather talk about some hardware details? How do you store a tree inside of something like this? Or would you rather talk first about the mathematical properties of the tree, of a balanced tree? Why search is fast. Okay, yeah. Very good. Perfect, let's do it. All right. So, again, don't confuse a data structure and an algorithm. Just because they have similar names doesn't mean that they're necessarily related. So we're talking about a binary tree, that's a data structure. We've also talked about a binary search, which is an algorithm. Okay, the binary search, you can do it on different types of data structures. You can do a binary search on a binary tree, but you don't need a binary tree to do a binary search, and you can use a binary tree for things other than a binary search. But it just so happens that in this case, the two marry together very well. All right. Let me pick out on a random volunteer. How about Aum? A-U-M?
Sure. Hello.
Hey. So first of all, I'm going to start drawing a tree. And I want you to tell me how many nodes are going to go on the next level. So at the root, we have 1. At the next, we have 2. How many nodes at the next level?
4.
4. Okay, and then in the next level?
8.
8. Okay, and what do you think the next level will be?
16.
16, all right, yeah. Do you see a pattern?
Mm-hmm. It's all squares of 2.
All powers of 2, yeah.
Powers of 2.
Okay. So that is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. Okay, very good. Now, just for naming conventions, I've had some students in the previous class ask about this. Do you call this level 0, or do you call this level 1? I don't care. I don't care. Just be consistent. Personally, I go with level 0 because of this. The number of nodes on that layer is going to be 2 to the level that it's at. So if you start with the naming convention layer 0, then that holds. The first layer has 2 to the 1, the second layer 2 to the 2, third layer 2 to the 3, fourth layer 2 to the 4. So that's why I prefer it. But that being said, if you like to call this layer 1 or level 1, whatever, fine with me. I don't care. Just don't go back and forth. Choose one and stick with it. Very good. All right, how about Jacob?
Hello.
Hey, how are you?
Good. How are you?
Oh, doing okay. So let's see. This might be a slightly harder question. I'm not sure. How many nodes are there in total in this tree?
31.
31. Very good. 31. Can you put 31 in terms of 2 to the something? Maybe plus or minus something?
That would be 2 to the. Mm,
Give you a little hint.
-1.
Very good. 2 to the 5 minus 1. So, in a full tree, the number of nodes is 2, the number of layers minus 1. Sorry, 2 the number of layers plus 1, because I'm starting at 0. Okay? For me, I'm calling this level 0. Again, you can call it level 1. I don't care. Just be consistent. Here, if you're using 1, then you won't have a plus 1 here in the exponent. But it's 2 to the number of layers plus 1 minus 1. That's how many nodes there are on the tree. Great. How about Jing Hao? Jing Hao? Li Jing Hao. I'm sorry, I can't tell. Maybe your mic doesn't work. I see you're unmuted, but I don't hear anything. Okay, maybe I'll roll back around to you. How about Marcella?
Hello.
Hey, great. So here, right now we'll just be thinking about full trees. Okay, so these are examples of full trees. Level, here's 2 levels, here's 3 levels. Or I'm sorry, here's 1 level here, whatever, 2 levels, 3 levels, 4 levels, and here we have 5 levels. What is the depth of this tree?
5 levels?
5. Yeah. Good. All right. So I'm going to, sorry, put you on the spot a little bit. I'm going to see, can you see a relationship between the depth and the total number of nodes?
It's the exponent that you do to 2, so it's like 2 to the depth minus 1.
Very good. All right. Now, this is, I hope that maybe this stands out to some of you. Because this is some crazy stuff. This is like super cool about binary trees. And I'll keep you on, Marcella, if that's all right. Okay, just because. Let's say we have 2 to the 10 nodes. I'll let you know that that's 1,024. Actually, let me move on to somebody else. How about Megan? Megan Ma. Oh, does your mic work? Again, I see you're unmuted, but I'm not hearing anything. All right. No problem. We'll come back. How about Shichuan? Okay, you're here. All right. Well, no mic. All right. Well, that's too many people without a mic, so we're going to go without a mic for you. You lost the draw. How long would an array be to store 2 to the 10 nodes, or 2 to the 10 numbers? Hopefully that's an easy question. $1,023. Yeah, it's actually 1,024. But if you're indexing it, it starts from 0. But who cares? Whatever. Stuff like that, like plus ones, minus ones. Who cares? I don't. By the way, don't freak out on a homework or a quiz or exam or anything with these like plus one, minus ones kind of nonsense. I don't care. It's like I don't know. Like I'm not going to like count you wrong for it. It's a rounding errors. All right. Now, how deep, this is also for you, Shichuan, how deep would a balanced binary tree be with 1,024 nodes? $10. All right. Very good. 10. All right. Now, thank you very much, Shichuan. Now, the thing to notice here is for a tree. All right, I'll try drawing a slightly deeper tree. Let's say, and I'm not going to be able to draw, I'm sorry, a depth 10 tree. I mean, I could, but I don't want to waste your time like that. How about Ziju? Li Ziju?
Here, hi, Professor. Can you hear me?
Yes, I can.
Okay.
All right. So I'm not going to put numbers in the tree, but imagine that there's numbers here, and it's a balanced binary tree. I'll put a number at the root. I'll put the number 10 at the root. Who cares?
Okay.
What do you know about all of these nodes to the right?
Could you repeat that question? Like,
Yeah. So because this is a balanced binary tree,
yeah.
here it's really the binary tree part of it. There's some property that all nodes to the left have, and another property that all nodes to the right have. So for these two subtrees, what do you know about, let's start with the one on the right, I guess. What property do all of these nodes share?
Property?
Let me ask a different question. Could I, let's see, is this, with these numbers, is that a valid binary tree?
Yeah. Oh, wait. Yeah.
Not by our conventions. Let me go back up here for a binary tree. Here. So this is what should hold true for a binary tree.
Oh, okay.
Right, so numbers on the left are different than numbers on the right. So for here, what's wrong with the number 11 and the number 6 here?
So, like, 11 should be right and 6 should be left.
Very good, yeah. So 6 would have to go on the left because it's smaller than 10. And
Okay.
What number did I have here? 15? I don't remember. Who cares? Would go on the right.
Yeah.
Okay. How about all of the other numbers here? All of these other numbers on the right.
Should also be greater than 10.
Very good. So all of these are greater, I'm sorry, greater than 10. And all of these on the left are less than or equal to 10.
Yeah.
Okay, very good. I'll keep you around for just a moment. Now, when we do let's do a search on this tree, okay? And it's a balanced binary tree. Let me fill in some extra numbers, I guess. 17, 12, 13, 11. Sorry, I'm writing really small. I'll zoom in a little bit. So here I'll put 11, 13, here, 18, 16. All right, that's good enough. Okay, you can see the numbers clearly enough?
Yeah.
All right. So for a binary search, how would we search for the number 13? How does that go?
So gonna cut
Where do you start?
from the middle.
From the root. Always,
Oh, yeah.
always start from the root. Which is,
Okay.
yeah, sure, you can call it the middle. That's fine. Okay. And now we're looking for the number 13. So how does that work?
So because it's like bigger than 10, so we should like cut the left half, and so
Mhm.
gonna find 15, and
Yeah, so you branch right. Yeah. Because 13 is bigger than 10. And 10 is
Yeah.
not 13. So if the number 13 is here somewhere, it's certainly going to be to the right. Okay,
Yeah.
now we're here at 15.
Yeah. So 15 is another sorry. Is
Let me
that
compare
is that
13. Mhm.
yeah, so yeah, it's smaller than yeah, it's bigger than 13.
Mhm.
So actually we need to like cut the right half, so we should go left,
Very
and
good.
again, is that 12? Is that
That's 12. Yeah.
okay? So 12 is like smaller than 13, so we should cut the left half, and then we can find 13.
Right. So 13 is bigger than 12. If it exists, it's going to be on the right.
Yeah.
Then you come here, you see, is that 13? Yeah, it's 13. So you return true.
Yeah.
13 is found. Or you could return some other stuff about its location. Who cares? The point is, like,
Yeah.
the algorithm, it's a search algorithm. Does it exist or not? And yeah, it does. Very good. Let me. Thank you very much. Good job. And I'm sorry, guys. Hang on for just a minute. Okay, guys, sorry about that. Here we go. Let me pick on a different person. How about Ishan?
Hi, Professor.
So I'm not going to. Well, let's stick with the same tree for now. Again, when we're oftentimes we care about worst case scenarios. So, in the worst case, how long would a binary search, take on this balanced binary tree, the one that's on screen?
Would it take 1/2 of the depth of the tree? Because you can immediately get rid of the left one.
So, what's the scenario for that? Where in the tree is the number that you're looking for? What's the bad case?
13. So it's on the third one if I start with 0 up top, 1, 2, and then 3.
So, if you stop here, that's the worst case scenario?
No, one below.
One below. Here. Okay. How long? So, for example, you're saying the number 13 here. That's a worst case scenario?
No,
many
the
steps?
worst case would be one more below that, so at the very end of the tree.
At the very end of the tree, right. So it's when the node you're looking for is a leaf. And this is true for a balanced binary tree. Whatever, it's the node at the deepest depth. Here we have all of these nodes, 16 of them, that are all at the deepest depth. So here in the worst case, you can just count it, 1, 2, 3, 4, 5. Like what is the number of steps that it would take for a search? We can just count it. Let's go for that one. That one's a bad node. Hello?
Yeah.
So how would we search for this? We're aiming for that node. That's going to be our destination. How do we get there?
So you would start at the top, right?
Yep.
And then you would eliminate everything to the right of 10.
Okay.
And then you would go to the left of 10, and then you would eliminate everything to the right of, that's a 6, right?
Yeah.
Okay, so you would eliminate everything to the right of 6.
Okay.
So now you would go 1 below 6. You would eliminate what's to the left.
Okay.
So then you would go to the right of that one, and then you would go to the right again.
Perfect.
And then you're at the final.
All right, let's count how many steps that took. So you check here, that's 1 step. And I'll let you continue.
All right, so that was the first. So then the next one is number 2.
Yep.
Then we're at number 3. 4.
Yep.
And then 5.
Okay. And what's the depth of this tree?
5.
5. All right, so the binary search worst case is the depth of the tree. Very good. All right. Now, for the math part of this, why is this so cool? Like for a binary tree. Let me go back up here a little bit. How long, in the worst case, for a balanced binary tree, does something take? It takes the depth of the tree, in the worst case. Here, when we're talking about the number of nodes, we're doing it in terms of 2 to the raised to the power of something. And the depth of the tree is that something. So if, I don't know how gigantic of a number this is, but 2 to the 1,000, all right, that's a gigantic, huge number. It's like basically, 1 with 1,000 zeros after it. Huge, big number. Like more than the number of atoms in the universe big. Like, no joke, big. Now, how long, I mean, we can't do this because it's more than the number of atoms in the universe. You can't even build a hard drive to store it. But in our pretend world on paper, how many steps in the worst case? Let me ask Ferna. You have a mic?
Yeah.
All right, so imagine we have 2 to the 1,000 numbers. In a balanced binary tree, what would be the worst case search time?
So n, so 1,000.
Yeah, perfect. Very good. All right, so that is to say, if you have n nodes in a balanced binary tree, search takes time log base 2 of n. All right? So, similar to when we were talking about the array, a search with n nodes takes time log n. Turn on my camera real quick. All right. So, the thing about a balanced binary tree is it's super, super compressed. All right? With 1,000 levels, which isn't so many, you can store 2 to the 1,000 nodes. I mean, it's a gigantic, like, number of nodes that you're storing in, like, a little, 1,000 depth, little teeny tiny tree. But inside of that depth 1,000 tree, there's a gigantic number of nodes. So, in fact, you are compressing all of the data by an exponential amount. Okay, so here's this, again, double-sided coin of exponents and logarithms. Because it's a balanced binary tree, then it's close to being full. And in a full tree, every single level is occupied. And so you can see the exponent, right? 1, 2, 4, 16, 32, 64, 128, 256, and you can go on and on. Each level, you're doubling the number of nodes that it holds compared to the level above it. In fact, the very last layer contains as many nodes as there are all above it, minus 1. So for a tree of depth, let's say 10, all right, in the 10th level, there's 512 nodes. The level above that would be 256 nodes, right? So you've doubled it, going from the second to the last layer to the last layer. But there's 512 here, and now if you do the math, above it, 256 plus 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, all of that is equal to 512 minus 1. All right, so every layer that you add, you are doubling the number of nodes that you have from everything that's above you. So this is what I mean, like every single layer, it's just like, this is a very, very highly compressed data structure. Is this worst case time for a binary tree or a binary search tree? Good question. There is no binary search tree. That's confusing algorithms and data structures. There's a binary search. There's binary trees. You can use a binary tree to do a binary search. But there's no binary search tree. This is why I'm trying to make the distinction clear between data structures and algorithms. you can do a binary search on other data structures. We did it earlier with an array. You have to sort the array, and once you have it sorted, you can do your binary search. And that binary search also takes time log n. So far, we have a binary search, and the binary search takes time log n. All right, that's what makes it a binary search. But when we were dealing with an array and just sorting the numbers, then when we wanted to insert a number or delete a number, it took a really long time. Time n, in fact. Let me scroll back to that. Here. So when we were talking about using an array, if you sort the numbers in your array, then you can do a binary search on it. So you know the length of the array. You go to the middle of the array. Because you know its length, you divide the length by 2, and you end up at the middle. And after that, you can make whichever side of the array has the correct side of the number, and then you reduce your search set to that, and then again, you cut that in half, and then again, you cut that in half, and half, and half, up to a maximum of log n times. So far, the array and the binary tree are equally as good for search. Each of these are log n.
Professor?
Yeah.
So the reason I asked that question is because, from my understanding, like, so the binary tree is just a tree that has, at most, 2 child nodes, right? Is that correct?
There might be a little bit more to that. I think it's not just that there's 2
Right.
nodes.
The
It's
reason-
that there's an ordered sequence, and for any node, you can either go left or go right. Like there's some sort of rule that you would follow to make something a left child or a right child. It's not just anything with 2 nodes, but maybe that's being pedantic. Yeah. What?
Yeah. Pretty much the reason I asked is because I thought there were trees. So I thought there were trees that were designed where not always the left subtree is less than the root node and the right subtree is greater than the root node. So like the reason I asked about that algorithm is because there are searches in like binary search trees where the trees are designed that the left subtree is less and the right subtree is greater. But then I've also like encountered trees where the left subtree isn't always less and the right subtree isn't always greater.
Can you say an example of that? Under what circumstance did you see that tree?
My internet bad?
So, I mean, okay, I don't know. Maybe this is getting a little bit too technical, but if there's no rule behind, the ordering of things, such that it doesn't have to be greater than less than, it could be some other property. I don't know, taller, shorter, alphabetically before, alphabetically after, something like that, where there's a differentiating factor, because that's how you benefit from a tree, is that you can start at the root and you know which direction to go. There's, I suppose, sure, there's trees that don't have that, but then that's a little bit of a different beast, and these types of guarantees that I'm talking about wouldn't necessarily hold. For example, it could be the case that you go left down a tree and now you realized that's not the right direction. So now you have to go back up and then traverse the right of the tree. And yeah, I guess that there's problems where that can happen. But that would not have the types of guarantees that I'm talking about. A search taking time maximum log n, for example. I would not be able to make that statement about if you want to say a binary tree without this property, where numbers can just kind of be whatever. Then this argument that I'm making about how fast a search can be done falls apart. Oh, by the way, there was another question here that I saw. Do non-binary tree exists, or are they a thing? Yes, they do exist. So the binary tree, it's just, it's the simplest tree. There's other types of trees. I mean, you could have 3 nodes, 3 children. Yeah, you could have a node with 3 children. That's called a trinary tree. So you could do this where, like, let's say if this is, I don't know, x, a, b, c, then here x is less than, or a is less than x. I don't know, let's say a less than, boy, how to say, well, you'd have a range. Like here, it's from, I don't know, minus infinity to, I don't know, minus 100. Here would be minus 100 to 100. And then here would be 100 to infinity, for example. So you could instead of having it be a binary range where it's either less than or equal, or I'm sorry, less than or greater than, you could do it in 3 and say if it falls in this middle range, then it's a middle child. If it's bigger than that range, then you go right. If it's less than that range, you go left. And you could do that, you could have a quadrary tree where now you have 2 ranges or 4 ranges instead of 3 for a trinary tree, etc. So yeah, there's definitely different types of trees. In fact, the B tree that we will talk about, is more like the trinary tree. But like I said, if you know the binary tree, I mean, doing that, I don't think that's a big mental jump to make. Basically, everything's the same, but like with a little tweak. So this is why I'm focusing on binary trees first, because we get all the hard stuff out of the way. And after that, if you're comfortable with it, just little tweaks. And now you can have lots of different other types of trees. I should also say that a tree is a subset of a data structure called a graph, where a graph, can be something like this, where you can have multiple nodes connected to each other. In a tree, this is not good because you can't have a child be its own parent or a child be its own ancestor, which would be the case in a graph or a general graph. So there's stuff like this. There's also like directed graphs, where you can't go from one node to another node in any way you like. You have to follow the direction of the edges. This is used in like map programs, one-way streets, arrows, two-way streets, edges. And then, you can have the cities and all the locations as the nodes, and then the roads that connect them as edges. You can have weights. If that's 10 miles apart, that's 5 miles apart. This is 1 mile apart. You can have weighted edges. Same thing on a tree. You could add weighted edges. And I mean, this is like a whole big field of study, data structures and algorithms that complement them. So yeah, but this, I mean, if you're interested in this kind of stuff, great. There's classes at Rutgers that you should be able to take for it. Data structures, algorithms, stuff like that. I'm just kind of giving you guys a flavor, a taste, enough to be able to put databases in context, so you actually have some deeper understanding of what's happening with them. And yes, the worst case runtime for I'm sorry, and so I'm emphasizing that these are for balanced trees, okay? If you can have a binary tree, but if it's not balanced, then you might as well be working with an array. Here, on the right, that's a valid, this one, that's a valid binary tree. But obviously, with this 1,000 nodes, in the worst case, it would take you 1,000 to go from the root all the way down to the leaf. That's takes 1,000 steps. There's 1,000 nodes. It's a big long chain, and you have to start at the root. And yeah, so the log n time that I'm talking about is only the case for balanced trees. Okay, because balanced trees have these extra benefits, these extra properties to them that we can exploit. It takes time to balance a tree. In fact, I don't know, only if you guys are interested, and I won't do it today, but I'm skipping past how to maintain a balanced tree. When you're building a tree, like keeping a list sorted, you also would need to keep the tree balanced. And it's not that hard. It's maybe 5 or 10 minutes of a few examples, but I'm afraid that might be getting a little bit too in the details for the purposes of this class. Just know that there's a fairly simple way to keep your tree balanced. Actually, I need to touch on it really quick. So I'm not going to go into the details, but I do need to touch on how that kind of works. Okay? Before I do that, let me call on Cole.
Hey.
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 So this is just going to be a review, but for an array of a binary search, what is the search time on that? Using an array.
Is it the depth?
Not the depth. This is for an array.
Okay. I guess n.
Log n. Log
Okay.
n. Okay.
Yeah.
Why is it log n? You need to tell me.
Is it because you break it in half each time?
Exactly. Very good. Yeah, and you can only break something in half log n times before you're only left with one thing. Now you can't break it in half anymore. You're already at the smallest thing. All right. How about, do you remember insert or delete? How long these take?
I would say it takes one step.
Let me go back up here. It takes one step for an insertion, for linear search, but for binary search, it's a little different. Hold on. Okay, we'll just go through it real quick. Here. So let's say we have this list, 1, 2, 3, 4, 5, 6, 7. Okay. And I want to delete this node, number 1. Can I just delete it and now I'm done?
No, I would guess no.
Okay, so why? What else do I have to do?
I guess kind of get rid of that empty space.
Yeah. Okay. How do you do that?
I guess that's just another step. Not sure how you do it though.
Let's shift every. Go ahead.
I guess you look to the right and then maybe break it in half again, or see if you have the results that you're looking for.
Let me start you off here. What if we move the 2 there?
Okay.
Then we fill that gap, right?
Yeah.
Okay, but now we have a gap here. So what do we do?
I guess just keep moving everything to the left.
Very good. Yeah. Yep, that's how it goes. So then there'd be 3, whatever, 4, 5, 6, 7. Yep, that's how it would go. So how many steps did that take?
Is that 7?
Yeah. So
Yeah.
n.
Okay.
I'm sorry, that's for deletion. N. Now for insertion, let's do the same thing. I want to insert the number 1. How do I do that?
I guess you would go back and add a box, and then, or I guess you have to move everything to the right.
Exactly. Yep. Now you got it.
Yeah.
So you have to move everything to the right. You can only add space to the right. 1, 2, 3, 4, 6, 7. All right. And how long did that take?
7 again, or
7.
N.
Yep.
Yeah.
Perfect. All right. Thank you so much. Yeah, very good. Good review. How would you move arrays to the right or left? That's a good question. Again, I don't want to get too deep into the weeds on these things, but the way to think about it is that you can grow space to the right, but you cannot grow space to the left. Loosely speaking, the way it works is this. Let's say on your computer you have, and I'm going to talk about RAM. Same thing with disks or whatever, but I'll just talk about RAM. So let's say you have 8 gigabytes of memory in your computer. Okay, so you already maybe can count how many ones and zeros that would be. Who cares? Excuse me. But you have 8 gigabytes of memory. Now let's say you boot your computer and you're using Windows. So Windows is going to be occupying some space in memory, Windows. Now you open up Microsoft Word. Okay, Microsoft Word is also going to be taking up some space in RAM. Let's say Microsoft Word, when it opens, it needs 500 megabytes of RAM. Okay, so Word needs 500 megabytes of RAM. Okay, let's just say that. So what you could do is to allocate exactly 500 gigabytes of RAM, or 500 megabytes, excuse me, of RAM, and then have Word go there, right? You're giving it exactly the amount of space it requires. But now maybe you're doing stuff, right? Like you're opening up certain features of Word, and now it needs more RAM, right? Maybe you need an extra 100 megabytes of RAM. Then you've only allocated 500 megabytes for RAM. So the way it would work is Word would tell Windows, I need 500 megabytes of RAM to run properly. And Windows would give not 500, but let's say 800. Right? So at first, Word is only using 500. All right? But there's a little bit space at the end of it, such that if the program needs it, it's there. And so you can grow to the right like this. You cannot grow to the left because the Word program has been shoved against the Windows, right? Windows is using this space. If you try to grow left, then you're going to have Word interfering in Windows space. So instead, every time you start a program, it will give you the space that you need at the beginning, plus a little bit of extra. And it's from that little bit of extra that you can extend your arrays like this. Okay, so this is why arrays can only grow to the right, they cannot grow to the left. Because if they were to grow to the left, then you would be overwriting things that don't belong to you. Yeah, that's more of like computer architecture kind of stuff. If you don't understand it, who cares? But that's, yeah, a decent explanation as to actually why it's like this. I'm not just making it up for fun. Should we just know as a concept that you can move them either way? No, yeah, you can't. Okay, I'll say this. You can only grow in one direction. If you want to make that direction left and you can't grow right, fine with me. That's a symmetric thing. Everything will be the same. But you can't grow both places. You can choose one or the other. The arguments would be identical, just symmetric. So I don't care. If you like things growing left, do that. I don't care. It's fine. Okay, so we have like 5 minutes left. All right, so I gotta talk about. I'll hang around if you guys have more questions about stuff, but for your homework, I gotta talk about at least one way of storing a binary tree inside of an array. All right. Now this is. I'll try not to rush it too much, but I don't want to keep you after. So. This is sort of a conceptual leap that you'll have to make, okay? I've talked about arrays, and we've talked about trees, okay, as two different data structures. And they're different data structures. But you can encode a tree inside of an array. Okay, I'll say it again. You can encode a tree inside of an array. Now, really quick, how that would go is, let's say, I don't know, 5, 3, 4, 1, 7, 6, 8. All right, so here's our tree. How are we going to put this tree inside of an array? Method 1. Okay, there's a different method. I'll get to that next week. Which, by the way, you can talk about either method in the homework. I don't care. Due next Wednesday. So you can use this one if you like. You can also wait until next Tuesday. You can talk about both. You can whatever. This is sort of the simpler way. And this is layer by layer. All right. Encode layer by layer. So what that means is here, layer 0. Put the number 5. Then the next two comes layer 1. And then the next 4, layer 2. All right, so we'd have the number 5, layer 1, layer 2, 3, and 7, right there, 3 and 7. So that's our second layer. And so we move our second layer here in that spot. All right. The next layer, the next layer, this layer, we have 1, 4, 6, 8. Okay, simple as that. Now, when you look at this array, you understand that this is a binary tree. Don't treat it like a sorted list of numbers. It is sorted, but it's not sorted from big to small. Right? Another way you could have sorted this in the array, the way that we talked about earlier, is saying 1, 3, 4, 5, 6, 7, 8. Right? Here is one way you could take these numbers and put them in a sorted array. This is sorting it from smallest to biggest. And you can do a binary search on this. Fine. But insertions, deletions take time. Here, this way, this is also sorted, okay? It's not random. I'm not just throwing numbers wherever I want. There's a reason why the numbers are going in this order. And the reason is because I want, layer 1 here, layer 1. Then I want layer 2 here. Here's layer 2, it comes right after. Then layer 3, the very last layer, is here. All right, now I have, if I maintain this, then it's a binary tree, right? There's no difference. There's no difference between the tree on the right and using this array on the left. Okay, they just look a little different. But I'm taking a tree and I'm encoding it inside of an array. So that's how you do it. I'll talk more about that next week. But last thing, why? Why? Okay, so first of all, binary trees are great. All right, they're fast search, fast insert, fast delete. I'll talk more next week about the fast insert and fast delete. So we like binary trees. We would prefer them over on the bottom left here using an array in that kind of way. It's better than nothing, but the binary tree is even better. The problem is that what kind of hardware can you have that tree thing? We don't. All this hardware here, all of it works like a big array. That's the way you think about it. Just like a big, 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 long array until you're out of space. So if we want a binary tree, but we're restricted to putting a binary tree on this kind of hardware, then we need to think about everything in terms of an array. And so that is why we go through the trouble of taking a binary tree and doing this trickery of encoding it in an array. That way we can use the binary tree in real life on real world hardware. Okay? So that's it. Thank you guys. You can log off. I'll hang around for a couple more minutes to answer questions. Let's start with the homework. How would you like us to write our responses to the homework? Edit the PDF you sent, the Word doc. Whatever you like. When you submit it, I would prefer PDF. Like even if you write it up as a Word doc, if you could print it off as a PDF, that would be great. Otherwise, you can handwrite it on paper, take a picture, upload the pictures. That's not my preferred way, but I understand sometimes things happen. So I prefer PDF, but you can turn it in whatever way. Yeah, just make sure you turn it in.